We live in a universe, and you might have noticed that the universe has stuff. And since antiquity, ever since people were asking questions about all of the stuff, they also had questions about what happens when you remove all of the stuff, what we would call a vacuum today. Now, the ancient Greek did not think it was possible for vacuum to exist because they thought it was impossible to fully remove everything from something. And very quickly you go into this whole thing of how can something be nothing and still be something? You know, the kind of shit you would expect from a civilization that couldn't invent zero. And this kind of wankery went on till around the 12th century when Al-Jazari, an Arab engineer who, among many other things, constructed the world's first vacuum pump, in that it was a suction pump that could pull water or really any fluid that relied on creating partial vacuums. Very cool, but also very not popular at that time because there were other kinds of pumps around that time that did the same job but better. Unambiguously, arguably, the first ever sustained vacuum ever produced in the world was made by Torricelli with his mercury tube in 1643. The way how this works is you fill a tube full of mercury, so there's nothing else in there, and then you flip it into a tub filled with mercury. Now, because gravity exists, the mercury will be pulled down, but because the atmosphere exists, the mercury will be pushed up. The net effect, however, involves the mercury coming down a little, creating a small pocket of vacuum in there. It's not a perfect vacuum, but it kicked off the race to create one. But here's the thing, we're doing physics here, and where we do physics, we need precision. The way how we think about vacuums is closely connected to pressure, specifically air pressure, because the more pressure there is, generally it means there's a lot of air or air molecules in there. Less pressure, fewer molecules. So everybody is trying to get rid of as many molecules as possible to lower the pressure inside their boxes as much as possible. But lack of air molecules does not mean a vacuum. It must be a lack of all kinds of matter. So a precise definition would be something like we have a box and there is absolutely nothing in the box. Now, what nothing means is complicated, but thankfully, we don't live in the times of Aristotle anymore. This time, we have math to clear away any miscommunications. According to the most modern framework of physics, everything is made up of fields, which can behave like particles or waves or whatever. So light, for example, acts like a wave sometimes and acts like a particle sometimes. But the absolute ground level truth is that light is an excitation or a ripple in the electromagnetic field. Similarly, an electron is an excitation in the electron field, and so on and so forth. So a vacuum would be a region where all fields, all of them, would be zero. There is nothing in there. But that's just a general framework. Let's look at a concrete theory that we know works. Quantum electrodynamics. No other theory we have predicts things to the same level of accuracy that this one does at time of recording. And in QED, when we say vacuum, we mean there is no matter inside, like electrons, but also, more importantly, there are no photons inside. And when we start looking things in the world of QED, we're gonna start running into some problems. Problem number one, the box exists. One of the first breakthroughs of quantum mechanics as a field is that any object that has a temperature will absorb and release radiation all the time. This is called black body radiation. So in order to ensure that there are no photons in the box, we will have to remove all of the temperature in this box, meaning get the box to absolute zero. But according to the laws of thermodynamics, you can't do that. It is mathematically impossible to achieve absolute zero. Okay, but we're in this weird hypothetical space. Let's assume that we have a box that does not do black body radiation at all. Some magical material, we don't really care about it. It's just a thing that separates the outside from the inside so that we can only care about what's going on inside. Problem number two. The rest of quantum mechanics exists. Because of a little something called the uncertainty principle, by saying that there is nothing in there, you are being awfully certain about the status of matter in that box. And you can never be that certain. And this is not just some
humans are bad at measuring
thing. I mean, the universe literally forbids it. And so what happens in this empty box is that quite literally, out of nothing, you can have what's called a vacuum fluctuation. Particles that appear out of nothing and disappear into nothing. Whoa there! Creating matter? Destroying matter? Sounds like you're violating some laws over here. And yeah, you're right. But also this is a consequence of the uncertainty principle, that technically for some very, very small periods of time, the variance in energies is non-zero. So that while the overall energy is conserved, it need not be for these brief bursts in time. It's kind of like this. The field itself can be zero, but that doesn't necessarily mean that ripples still can't form on them. Except nothing is causing the ripple to happen, so it's kind of like the ripple just forms out of nowhere and then disappears out of nowhere, and it happens faster than the universe can check. If you're not convinced by that explanation and know a bit about physics, what I'm basically saying is that the expectation values for the electric and magnetic fields in the box are zero on account of there being nothing, but QED predicts that their variance would be non-zero, and generally you get particles in there when that happens because of the damned creation operator. If you're not convinced by that explanation and don't know that bit of physics, my sincerest apologies. Please forward your complaints to shrug@facebookmail.co.uk. Even theoretically, in the purest of the pure hypothetical setups, it is impossible to have a pure vacuum. But unlike a lot of quantum weirdness you hear certain people peddling, we've actually seen this effect with our human eyes. Okay, kind of. We've observed the effects of the void actually not being empty. Because these fluctuations are in fact particles, and particles interact, we can tell if something is going on. When, say, these phantom particles interact with an electron that's part of a hydrogen atom. You might know that electrons go around nuclei and can jump up and down energy levels while absorbing and releasing light. That's what makes up an atomic spectrum. Well, because electrons can interact with nothing, it introduces teeny tiny shifts to these energy levels. The fact that the nothing wasn't empty makes a gap between two of these energy levels slightly bigger than normal. And this is called the Lamb shift, and was actually measured in 1947. Another way we know this is because of a little something called the Casimir effect. It's a complicated enough topic that deserves its own video, but long story to a medium-sized story, you put two ginormous metallic plates in as close to pure vacuum as you can get it really, and you get it really, really close to each other. When you do that, these phantom particles get created in empty space. The properties of these particles get limited by how much room there is in general, especially between these two plates. Like outside the plates there are no restrictions, but inside the plate there's simply not enough room. So on average, there will be more virtual particles outside than inside, and so on average, there will be more particles bumping into the plates from the outside than from the inside, which means on average, over a long period of time, you will notice these two plates move towards each other, even though ostensibly they're in pure vacuum. Is it more complicated than how I've explained? It absolutely is. Is this the explanation that everybody uses for the Casimir effect? Right again. Am I actually going to sit through and explain how Casimir and Polder managed to figure this out? I mean, I don't have a problem with it. I just don't think me walking through a QFT derivation makes for very interesting content. Or maybe it is. Let me know if you're curious down in the comments. Okay, fine. I just wanted to know if a pure vacuum was possible. I don't want to know any of your quantum weirdness. And yeah, you're right. It is kind of a cop-out to ask a hypothetical question and then just answer it with quantum weirdness. Although, generally speaking, when you do have a hypothetical question in physics with a superlative in there, you're going to find some weird shit happening very quickly. Sorry. Right now, at time of recording, the closest thing we know to a pure vacuum is the vaguely described outer space, which has an estimated 1 atom of hydrogen per cubic meter. By comparison, air at sea level contains about trillions and trillions of atoms of anything, really. By comparison, the Large Hadron Collider has some of the best vacuum chambers in the world, and it's right now comparable to what you would find on the surface of the moon, which is very close to nothing. And we're only going to keep finding ways to get to lower and lower pressures, but never truly zero. And in that sense, the ancient Greeks were right. They just didn't know why, and had absolutely no way of finding out why. Task failed successfully!